of our bigger operations, copper operations in Brazil. The size of this blast was around, well, the consumption of explosives was around 1,000 kilos per hole. So the operation this is a huge operation. Inside the video is just to help you guys not always sleep after lunch. I think we can have a little chat before starting. Before starting the presentation, I would like to know, just to have a better understanding about the operations here in Guyana, what would be the most common type of explosives you guys use here? Would it be ankle, packet emulsion, or the cartridges? What would be the diameters, hole length? This is the most common explosive used here, Magnum. Perfect. I was talking to Dave, and it seems that for the coming years, the mechanization will be something that you guys are going to be working with, hopefully. So, in the next presentation, we're going to be talking about priming and some of its aspects. Okay, I'll keep playing these movies later. We're going to have to stop and talk a little bit then after this presentation. Okay, so okay, Dave was asked to ask you guys to not forget to fill in this form. So after you finish filming, you can return it to us. So I don't know, I'll leave it here. You guys can pass it. You guys can pass it through the other tables just to check if everyone has filled it. All right. Just 1 second. Okay, so Brian. So, up to now, during the morning, we were talking about type of explosives and some aspects of priming. Andrea had a introduction about the different type of products, and for now we're going to be talking about priming. And by the end of this chapter, hopefully, you're going to be able to have a good understanding about the priming theory, the effects of primer type, detonating force effects, double priming, and primer decked charges. And hopefully we're going to be able to answer the 3 basic questions. First one, what is a primer? Second one, why do we prime? And third one, what would be a good configuration of primer? Right. So, to have a good understanding about what would be the consequences if we do not prime properly. If we suppose that we got a misfire due to a bad priming procedure. So I have a question for you guys. What do you think would happen with a misfire hole around here? What would be the consequences, cost-wise? Any ideas? Please, there's no wrong answer to this one. Oversight, excess vibration, what else? Come on, you're already sleeping. I had just 5 minutes of presentation, you're already sleeping. Yes, exactly. That's a good point. If we had a problem in the accessory, the surface accessory, this part of the glass might not go off. It's a big issue. What else? Any other ideas? I wrote something down. For example, we might have oversized fly rods, vibrating cutoffs, back brakes, productivity loss, wear and tear due to the larger fragmentation you might get from this glass. You might have a more wear and tear from your loading equipment. What else? Lost times money. You might have another misfire. Well, there's plenty of consequences. There is a bad priming that can cause a misfire, might cause to your productivity, to your operation. So, just a quick review. Andre already explained a little bit about hotspots and all that stuff with the fancy names. So, why? That's what we are trying to do with this picture is to answer the first question: why do we prime? Why is it that important? And the reason is here. I'll explain first what is this picture. Here we have the rock mass. This part here in red is the detonated explosive. As you can see, I don't know if everybody can see from the back, but there are some circles that's changing its shape until it gets a flat shape. And here there is a reaction zone, and these little stars is what we call hotspots. And what's happening here? Why it is important to prime, and what it's paper during the detonation. As Andres said, we use primers so we can make sure the explosives will make it work. So, and what is the consequence of it? If you do not prime properly, you might lose some of energy the explosive is supposed to give you. For example, if you do not prime properly, you might lose some of its VOD, the velocity of detonation. The implications of it are you might lose some of pressure, detonation pressure. This detonation pressure is responsible for breaking the rock and for all the heat. So let's get back to the picture. So here we have a primer. And this primer, when it goes off, when it detonates, it produces a shock wave that travels through the explosives and through the rock. And the main idea is that when the primer detonates, it creates a sort of spherical shock wave that travels through the explosives and the rock. Once it travels along the column, it has a spherical shape. And the ideal primer is that when it travels throughout the column, it gets a flat shape, so we can get the most of the hotspots. So this reaction can reach its maximum velocity. So that's one of the reasons we prime. An example of hotspots. I don't know if it's going to play by itself. Let's see. Well, it's not working. Yes. So as Andrea said before, once this shockwave travels through the explosives column, it compresses its little tiny bubbles, and when this bubble is compressed, it releases a huge amount of heat, and this heat is the responsible for keeping the detonation reaction going. Alright, so what? Why is this VOD so important? As we said before, the VOD directly related to the detonation pressure. And I forgot to write here what would be the equation for calculating this pressure. But the pressure can be calculated by taking account 2.25 times the explosive density times the VOD squared. So the VOD plays a very important role in finding the detonation pressure. In this table, we can see, just so you can have an idea about what will be the detonation pressure for the different type of explosives. Here we have Pentex, which is the most common booster, and everyone have already worked with this type of explosive here. Shot fires. Yeah? No? Okay. So, as you can see, specific gravity, some people might call it the density as well, there is a small difference. That's not the case. The Pentex has a specific gravity of 1.7, and it gives a 24 gigapascal of pressure, detonation pressure, which is almost 3 times higher than the Sentinel magnetic pressure. And why is that? First, the Pentex has a velocity of detonation of 7,000 meters per second, and the Sentinel has a velocity of 4 to 5, it depends from the situation. An average of 12.5. In the other products, they have pretty much the same velocity of the detonation. As you can see, there is a huge difference when you take into account the velocity of detonation of each explosive. So, in your opinion, what would be the best primer size? How would you choose the size of your primers? What you should take into account for selecting them? Here are some aspects that we should take into account. First, that's an obvious statement. Bigger holes need bigger primers. And why is that? Let's take, for instance, this one here. It's a glass hole with a small diameter. In this case, just remember, when we said few slides up before, the idea is that once the primer detonates, we can get a flat shape from the shock wave. Once the idea is we can get a shock wave in a flat shape as fast as we can. So, for the small primers, some of these waves can be reflected. from in the wall, in the glass wall. So it might help you get a sort of flat shape in this area. Once when you're using a very small primer in a big hole, this might not happen or might take a little longer to happen. So the idea is that you can use a bigger one so you can have the same sort of effect in both scenarios. And what else? Which one would you use? A MagnaFrac or a booster? I think that's. And what about the primer shape? The idea would be a spherical one. But I'm pretty sure we will not produce one spherical one. So what you're going to find in the market are boosters of this sort of shape. Well, so the idea is that actually shape doesn't matter too much as long as you compare from those different type of boosters. But when does the shape matter? When you're using the dead quartz as a primer or connected to a primer, what is the difference between those 4 primers to the dead quartz? Just bear in mind that the dead quartz has a primary explosives as well. The dead quartz has the same explosives as the booster has. Also the Then, why we should not use dead quartz, only the dead quartz as a primer? The idea is what might happen if we use the dead quartz with ample. You might connect another primer like at the top and use that quartz. But what might happen if we use it with ample? In ideas, that's one thing. You're not going to initiate your ample column homogeneous. You're going to have different points of initiation. And what else? You might not even initiate properly the orbital. And what? Yes. That's another thing as well. And the other thing, you're going to lose some of its energy, as you're not giving the proper energy to initiate your explosive, so it might deflagrate or just burn, and you're going to lose at least, in some cases, you might lose 30% of the energy by using that core. And any other primer, for example, if you use the combination of that core and MagnaFrac, depending on the diameter you use, you might lose at least 30% of its energy when you're using ample. The same goes for the pump emulsion as well. But it's more critical when you're using ample. What else? That's what we were talking about. And there are some other consequences. What do you think would happen to stemming when you are using that quartz as a primer or something, something to lead the energy from the surface to the primer on the bottom? You might lose some of your stemming. Yeah. Okay, what else? Well, some of you already said top of charge initiation. You can have variable energy releasing in your ample column. And and besides, you might, if you're using delays, you might have a bigger variation. And as we said, BOD, don't. That's the main thing here. Do not mess with your BOD, otherwise you're gonna lose energy. All right. So, in your opinion, what would be the best primer in this situation, considering, well, this plasma goes up? Let's consider what happens only in the first half a meter when you're using the same diameter and different types and size of primers. First scenario is that the pipette, 200 grams, Magna Prac, 1 kilo, and a small plate here is 100 grams. Which one do you think would be the best? Remember, there's no wrong answer for this one. And another important information, we are using info. Ideas? All right, let's do it differently. What do you think is going to happen when we are using pendants? Energy-wise, considering 100, as Andrea said before, 100 is the energy released by the ample, which is our standard explosive in terms of comparison. And the pendants, I'm not mistaken, is around 50% of the energy compared to 1 volt. So, in this graph, what we are trying to show is when the booster detonates, it releases a huge amount of energy. When it initiates the ample column just around it, when you sum both of them, you might get 107% of energy in this area, and then it goes increasing up to half a meter until we reach only ample energy. And what do you think is going to happen in the second scenario? Something similar. Remembering, this is emulsion and ample. And the emulsion has around 140% of the ample energy. Alright, remember, you're using almost 1 kilo, almost half a meter of magnet. Alright, so that's what we expect to have. A sort of 100 homogeneous release of energy related to the magnet trap. And then, when we reach half a meter, it gets back to the 100% of energy of a temple. And what about this small one? That's definitely not the ideal situation. So that's what we are expecting to get. So you're having a very low amount of energy released, in which we won't initiate properly our ample column. In other words, you're going to be losing energy pretty much from the first half a meter up to the 100 meter when the explosive reaches its steady state detonation. Once again, what is the main reason why we use primers? So we can give to the explosive most appropriate environment for the explosive, release the most amount of energy it can release, which is not happening here. See? The other question: what will be the most indicated way of priming. Bottom or top? There's no wrong answer. Bottom. Anyone else? Bottom, top? Top? And what will be the difference? Yeah, that's one point. That's one point. Well, you think there would be any difference regarding the heat? How would be the mud pile? Maybe. And the answer for this one, anyone? Actually, fragmentation-wise, there's no big difference. Well, it depends from place to place, but this exercise just to get you guys more involved with the presentation and to show and to talk a little bit about the moment. Just remember, all these pictures, they are exaggerated. So probably, even if you make bottom or top, you might not notice any difference in your mud pile depending on the situation. But the idea here is that when you use bottom primer, that's the sort of movement you are expecting to have. And when do you want this sort of movement? Why? It depends on the type of loading equipment you have, isn't it? If you want a higher mud pile, you have it, or it is specific on one type of equipment. When you want a sort of more flat mud pile for another type of loading equipment. And the top one, this is over exaggerated, but that's the main idea. And we might get some difference in fragmentation depending on your geology. Is that you might get an idea. What's the word for that? Yeah, it seems to be a little bit harder to dig at the top, and you're using one as opposed to the other. All right. Let's see what is the next stop. What about the time? All right. So, guys, if you do not understand anything I'm saying, or you have any difficulties regarding my pronunciation, please feel free to let me know. Right, I'll do my best to explain again. All right. So let's move on. And what about the number of the primers? Under what condition might we want to use more than one primer in a hole? Yeah, depending on the depth. What else? When you have cavities, good one. What? Steam. Oh yeah. I'm going to show you in the first. This is like. So yeah, there are several reasons for using more than one primer. Here are just a few of them. There's three situations. First of one, when you have a very jointed rock mass, what might happen when one whole blast hole detonates? It might move blocks around to the other holes close to it. And what might happen? You might have a cut in the continuity, your explosive continuity. So when this explodes, when this primer detonates, the detonation will be interrupted by this cut. Is when you have some steam going through through the glass hole, or when you have a joint where the water can flow through. So this water might wash off this explosive located here, or create a sort of water bed that won't let the detonation pass through it. And then we have other things that might happen, especially here. I think this is a very rainy area. Probably you're going to have lots of water inside your blast holes. And what might happen, you might get some slush or mud at the bottom of your holes that will not let the detonation do its work. All right. So when we are doing a double prime, let's see here. All right. Let's talk about it first. Okay. And what about the location? Where would we prime? When we are doing bottom prime, we just leave it at the very, very bottom. We lift it a little bit, a little higher. Or when we are using two in ideas, which one of this one here would be the best one, and why? That would be the most important word. Why? Which one of these ones here would be the best one to be doing? Which one would you use? How would you prime? And why? What do you think might happen in this situation here? Remember this last one here. Right?
I would just big reason it's always best when you're priming the hole, the booster should be up the very bottom, and in the board.
Yeah, exactly. And the other reason is that you might have some slush down the very bottom. And this one here might happen when you're, because of the water, when you're putting product, you might have some of the products here might be pushed up by the waters. And what about the E and E? We're going to be talking about them in the next slide. What do you think would be the difference? You're not taking account for now the dispersion related to the non-electric accessories. This one, when you compare D and E, what would be the difference we are using here? Remember, the delay number 12, the same, and here there are a small difference between them. 12.5, there's no delay with this sort of number. It's just to explain something. If we have the same delay and we are not taking account the dispersion between them, that's okay. But when we take into account the dispersion between them, what do you think might happen here? They have the same delay number, but are they going to fire at the same time? Usually we have a 3% dispersion in all kinds of non-electric accessories. Here's just a very basic comparison. This delay number 12 has a nominal firing time of 400 milliseconds. But it might fire from anything in between 403 and 397 milliseconds. So what could happen here? Let's say the first one fire at 400 or 397. So, in how long it's going to take from this shock wave to travel from here down to the bottom, considering 7 meters, traveling at 3,000 meters per second. It's going to take already all the math. So it's going to take only 2 milliseconds, which is faster than the delay, the time in which this delay here is going to be to fire. So what I'm trying to explain is that when you're using 2 primers, you might have a situation that this primer won't be initiated by the non-electric, by the exo. It will be initiated by the column of explosive. So what we should take into account, the length of the hole. And if we are using it, we should use at least one stem here to avoid this sort of situation. And why? As we said before, we need to provide a perfect environment for the explosive to release most energy it can release. In other words, if this part of explosive here, for mud pile, vibration, wall control,
when you've got horizontal wing.
that's a good one. Or when you find, for example, a cavity, for example, you have to use a stem in between or something that separates the cavity from your chart. And when this is very common forests in Brazil as well, when you are operating very close to the communities, and you have to have a very restricted control of your charts. That's one example when you use delay between them, so you can get a better vibration control. The other question is when and why we fire the bottom first and the top first. And again, there's no wrong answer for this one. It's all depends. In ideas, has anyone had to do it before? No? Alright, some people might say that there is a difference in the heat, as you can see from the pictures. In this situation, the bottom first, you might have a mud pile with this sort of shape, and probably you might get the toe area a little bit easier to dig. And this one, you might have a sort of flat mud pile, but it's going to be a little bit harder to dig at the toe. But as we said before, it all depends. Every mine site is different. So what works for one might not work for the other. These are all general rules. So, and when you have to use deck charts, what would be the rule of thumbs, or what we have to have in mind? Here's just a few tips. Of course, use it with care. Use it not standing. And why is that? So your chart that fires first do not the same size the top one or the bottom one. I think the first one, when you take care of this one, it's because you want to avoid both things here. Alright? You guys ready to sleep or just to check? I don't know, after lunch is a little bit complicated. So, what is the difference when we prime? Well, let's get a little bit more deeper in this subject. You guys already responded why and which one is the best one. But here's just a quick explanation why we should use the primer when energy-wise at the grade level and as opposed to the toe, the very bottom. So here's an explanation that we might have more energy directed to the toe, this part here, so breaking a little bit better than in this situation where some of your energy might be dispersed around on the rock mass. No big deal. It's pretty easy to see by this picture. So far, any questions? No? We are getting close to the end of this chapter. Just a quick summary of what we covered during this last hour, I think. So we went through the priming theory, effects of prime size and shape, effects of dead force, double prime, and double charge. You can find more information in the books right in front of you. It is a very, very good book. Very good. You can find a very detailed information. Any other thing that you might come to your mind later on, please feel free to drop us a line. If not everyone got our email, please let us know. We can give it to you later. Well, regarding priming, that's all for now. Next topic, if we have time. I don't know. No? Okay. So maybe we can. All right. So we still have 30 minutes before our coffee break. So let's start this subject. And once we get to 2:30, please let me know we can have a quick break. So we're going to start talking about charging block focus. Before starting this presentation, for the previous presentation, I asked you about what would be the most common charging block focus here in your region.
Before we go far, so far, all the example that the demonstrator will show us is here vertical drilling from exposure. What about horizontal?
Sorry,
Drilling. It's here vertical that you have drilled so far. What about
horizontal hole for priming. For priming, you lost. But it's not a very common practice for object tests. I don't know if we can talk about it. Are we going to be talking about the elliptic?
You mean when you drill in the bottom of the bench? Okay. We used to do that, but we had some incidents. When you don't have a good drilling control, you might drill and this horizontal hole in the bottom, they find the other hole from the bench, the main hole. And then when you charge, if you have delays defining different timing one hole can blast and initiate the other, may generate an accident or fire, or even you might have so many explosives concentrated in the same region, and it can generate a fire. We had some incidents in the past, and the miners stopped using this practice. It's better to have good quality control in the drill from the top of the bench, control the sub-drilling to have a good performance. And then you avoid doing this horizontal focus.
Yes, thank you. All right, can we move on? All right. So, charging block. So, as you guys told me, what is the most common practice around here is just to use Magnafrac. Yeah. Which length and diameter? Okay. So we're going to try to emphasize a little bit more when we get to this topic. Because here in this presentation, we're going to cover all the mechanized charging, as well as we're going to talk about loading with ample and using cartridges as well. Okay. So first, there are a few things you should to bear in mind when we're about to initiate our charging. First one, before starting it, what should we do? And it is, we need to adhere and throw some ideas here. First, obviously you have to think ahead. And what do we mean by that? When you think ahead before starting your charging, before charging. So you have to know exactly where you're going to be charging. How are your access? If you're using trucks, are you going to be able to reach this bench using your trucks? That's a good point. So what else? Do you have all the plans? Do you know how many glass holes you're going to be charging? What is the diameter? Any different diameters on your bench in the same glass? Yeah, that's a pretty common. Unfortunately, this is pretty common to have in some mines. Sometimes they used to mix different diameters at the same glass. So if you're prepared and thinking,
it's not a good practice, but sometimes it happens.
Yes, it happens. So, in this case, if you are thinking or if you are prepared to load a certain number of glass holes with a certain diameter when you get to the bench, and you have a different diameter, for example, you might end up having to reload your trucks, or you might end up having to take all the rest of the explosives back to the magazine. I don't know how it works here in Guyana, but in Brazil, in some parts, when they buy our explosives, we go with our trucks and we have to get a license from the army to transport. So if we do not use all the explosives, we have to get another license to transport back this explosive. So this is a big headache, believe me. I don't know, maybe you guys have something similar here? Transport-wise? Yeah, no. That's a very... You have to know exactly what's going on in terms of explosives, what is being transported. All right. So, and what about talking about before stop charging. And what about during? What should we do? What are the things, what are the key points when we start really charging our plastic? Our bench, can our bench have lots of junk on things we should not need? People wandering around that they are not related to the glass group. So that's one thing. And the other thing is when you use it, it comes emotion. Andrea was saying earlier this morning that we use this is a product that in order to become an explosive, you have to sensitize it. But and in order to sensitize it, you have to add some other product in this emotion. And you need time for this reaction to occur. So if you do not give enough time and care, probably you might end up with a misfire because your explosive is not sensitized yet. What else? Do you know exactly what volts you're going to be charging, how much you're going to be charging? If your holes are, if you got wet holes, dry holes, so these are all the things you should be in your head before and during charging. Let's go through this point. Oh, that's what you were talking. So first, here the area of junk. Check tape. This is a very important thing. So you can measure your holes and see where is the water lane, for example. Mark it like wet holes. I think here in Indiana, probably 100% of the holes will be wet holes, or not, or almost. Yeah. All right. No special glass holes. What would be this special glass hole if you had one glass hole that was not planned in your bench? If that would be a special one, because this one wasn't planned. But sometimes the operator, the drill operator, for some reason, they choose to put an extra one. Or for a good reason. If someone is blocked, if some glass hole is blocked, you have to re-drill it. If you're not able to re-drill, you have to put another one. And this would be a special one, an example. Unusual conditions. What would be unusual conditions? Any idea? If it's raining too much. Lightning. Yeah, exactly. All right, anything else? Yeah, that's, I think, I'm pretty sure you guys have a lot of lighting here in Indiana, I think.
You might find a hole in some soft material.
It might get blocked. Okay, this is very important, having loading plan, and obviously communicate. This is the most important part. Communication. Sometimes, for example, if you're charging, you have your charging area, and you do not communicate with your drill crew, and somehow you end up with a drill rig on the top of the bench in which you are charging. What are the implications of it, safety-wise? Drill rigs too close, you might reach some of your explosives. When you drill, for example, in the worst case scenario, and some of the drill rigs might fall as well. One of the pole, for example. It already had it. So this is just a few examples of communication. And as you were saying, another thing when you're using a MMU, the mobile manufacturing unit, this is very common to drag the holes around. And when you're doing that, you might drag some of the debris that stays close to the collar inside to the glass hole. And here are just a few examples of how we can avoid it. We can use a sandbag, for example, a foam, or something like that. Well, now I forgot how to say it in English. But that's just a few ideas. I don't know if here you have any other procedure to protect your glass hole collars. No? Pipes. That's it. Interesting. Good for small diameters for 3.5 inches. That's a good idea. That's a good one. I'll take it to Brazil. All right. So obviously, that's one thing you have to prepare before starting your charging. Once you get your trucks or your crew on the bench, probably they're going to be wandering around, laying out all the products. Some might just trip over a pile of debris close to the power and push some of this material inside the glass hole. So this is something you have to do prior to charging. Here is something pretty basic. I won't spend too much time on it. So what we should do? What would be the procedure for charging the hole? First, obviously, check the short fire spec. Then, lay out primers, priming charge web holes. Well, in our case, in Brazil, in which we have, it's not all sites. My site, we have 100% of the web holes. We used to start priming and charging first the web hole. And why is that? So we can make sure once some of the water inside the web hole might flow through the dry ones once we charge it. So that's one of the reasons we always start first with the web holes. Well, at least we try. And the other thing, once we charge the wet holes, we recheck the dry holes so we can double check if those holes are not wet now. Priming charge, dry hole instead of top prime, and then put the explosives instead. It's just a quick diagram showing how to insert the detonators inside the fragment, inside the booster. Self-explained. And what about this one? What are the procedures you guys have here when you are assembling the primers? And does anyone use the fuse to hold the cartridge? No need to answer. This one I don't want to hear. All right. So always the procedure is always have something hold through the cartridge, and then you can insert your detonator. Here are just a few examples of how you can tie it with your explosion. Here another example, you can use a tape. And in this one, you can use just a twist a little bit, and then poke the detonator, put your detonator inside your cartridge. just a quick reminder, do not use any knots around here, so you might damage your signal too. So here,
Can you go back one slide? Just for safety, when you are assembling the detonator inside the booster, if there is something that is difficult for you to assemble the detonator, don't push. Change to other booster for safety. It's not good, or maybe some debris or some rock fragments, but clean it first and then assemble the detonator.
thank you. What about the time? Are we ready for the
15 minutes. 15.
Okay. I can see some hungry faces. All right. So, and I'm pretty sure this is a very common situation here. That you can use the packet and then, if possible, ample. Is that right? Okay. So let's do a quick exercise here. Imagine. Well, actually, the exercise will be the next one. So let's do. So when you have a small amount of water at the bottom of your glass bowl, this is exactly what might happen when you're stop charging. Obviously, you have water and you put something else inside it, the water goes up. And this is the most indicated procedure when you use cartridges and ample. So first, obviously, you're going to put all your emulsion here, the packet emulsion, until you pass it through the column of your water column. And then, if needed, you can complete it with your ample, and then stamp. And what would happen if you do not do that? Just use a primer and ample. And let it sleep for 1 day. It will dissolve. Some of this ample will dissolve in the water, right? And when it dissolves, it gets it reduces its volume because you have fluids, small balls, and then when it starts dissolving, it becomes liquid. And obviously, you're gonna lose some of its volume, and you might end up having an air gap around here. Okay? Alright, so this is the exercise I was talking about. So, first step is pretty obvious. First, we lower our prime. Then we have a little bit of water here. This one is pretty easy to do, isn't it? So you just fill, and you lower it. When you reach the bottom, leave it there. And what about the next one? The next cartridge, next package. What do you guys normally do? Just leave it from here and let gravity do its work. And when you do that, what might happen? Oops. That's exactly what Andrea was saying earlier this morning. You might, if you do not take care when dropping your packet, your cartridge, you might have something. You might not have something like that, a water gap. And what do you think that might happen when you detonate this charge here? Will be flying explosives. Has anyone seen it before? Or has anyone found some rest of the explosives in the mud pile intact? Yeah, probably this might be one of the reasons. So, and what can we do to avoid this kind of problem? With care. Push it with care. Or you can lower it with care. You can use this one, your primer, as a lead. Yeah, that's one idea. But if you have to push it, take care. This is small push. Try to do this one using this as a lead. Let me see. What else? Okay. Let's go through this situation. In this scenario, we have similar to the previous one. We have a little bit of water. And from here, we're going to decide which product, which explosive we are using for each scenario. You can use any one we want, even the ample, as long as we take some precautions. For example, if we do not do anything, just put ample inside a wet bowl, we might end up having something like that. A salt ample, somewhere, something like that. And obviously we're going to lose lots of energy, or probably this glass bowl will not dip. And the second scenario, if we take all the precautions of loading this hole with heavy ample, yeah, we might, if we de-water, for example, we can use heavy ample in a combination below 30% of emulsion, 70% of ample. But what happens if we leave some of this water inside of the glass bowl? We might have some small pockets of water inside of this column. And how does it affect the explosive? Here's just an example. If it's supposed to have 190% of energy, when compared to ample, we might have only 60%. That's the implication. And what about pumped emulsion? That's exactly what we expect to have. When we start pumping properly, what we want is to push the water upwards. But what happens when we are pulling the holes too fast? We might leave some of this water behind. So, and obviously, there are consequences, which is losing energy. On the other hand, if you're really willing to use ample, yes, you can use it, taking some precautions. For example, you can use the gas bag. Does everyone know what is a gas bag and how it works? Well, yeah, there is several types of gas bags. But the main idea is that there is a plastic bag with some products. One is vinegar, also, and the other one I forgot the name of in English. And when they react, they release a huge amount of a gas. And they expand inside the hole. So they create a barrier separating water and explosive and ample. When you take this precaution, yes, you can use it ample. But you might lose some of the energy related to the length of explosive you could be using. Alright, so what about these scenarios over here? As we said before, the first option, you can always de-water, but when you are working in a raining area, like here, or when you have lots of water, probably, and have to to do it several times before start loading. And what can you do? You can use liners or this plastic slits over here. You can use it, but you have to take into account the price and the time. It's a little bit time consuming. And here is exactly how it would look like. The other option is to use after the one with heavy elbow, or the other combination of heavy elbow and elbow. In between, depends on what product do you have available in your mindset. And the other option here, only heavy elbow. These energies, they are varying because in order to provide some water resistance to these different products, you have to change the amount of input and emotion proportion. The more emotion you use, the more water resistance provides the product. Here are some examples of gas bags. And what is the implication in terms of energy? How you would expect sort of, what's the name of it? This area of influence. Yeah, we can call it area of influence of this, each scenario. When we are using ample and a gas bag around here, when you compare to when you're using, remember, here are the same amount of kilos of explosives. Notice the difference between the length here and where the water are positioned. And here's how the difference between how the energy, this is the energy distribution. And the other scenario is the combination of emotion, vortex, water, a gas bag, and ample. What is the implication of the energy-wise? Is how the energy would be distributed. Well, this is only a few examples of how we could use gas bags. All right, so. Right, for the first one a little bit hungry. We're gonna make a quick break, our coffee break. We're gonna get back in 30 minutes. Yep. Right, people. Thank you. Okay. Are we all there? No one else? Do we keep going? You all awake? All right. I'll try to go as fast as I can in this session. All right. So we were talking about pump emotion, and what precautions we should take when we start pumping glass holes with water. Here are some examples what we should be doing. In this case, just an example. So first, as we said before, when we are using pump emotion, first, it isn't a explosive until you have the sensitizer on it. But once you put sensitizer inside it, you have to give it time to let this reaction occur. So what's going to happen? You're going to produce small bubbles inside the explosive. And what is its implication? Obviously, we're going to have a expansion the explosive will expand inside the glass hole. So that's what we are expecting to get. It's just a quick reminder. Once you pump all your explosive inside the glass hole, just lift it a little bit so you can get it off from the sludge that stays right here. So that's what we expect to happen. So what is the time? How much longer do we have to wait before standing here? Before we put our standing on the top of it. Any ideas? Once again, it varies a little bit, but as a rule of thumb, if you can give at least 30 minutes for each bowl to get, that's the idea. So, and why is that? I'm going to explain it in the next slide. So this is here just an example. What if in a case in which we decide to use two primers? For the same very reason, we have to be careful. When loading the explosive here, we have to make sure that the primer will be surrounded by the explosive. We have to have the same precaution in this case here. So what we should do, instead of letting to put the primer at the end of your charging, you save some few meters, maybe a meter here, lower your primer, and then you can pump on the top of it. It's just a good practice. And what is the other precautions we have to have when we are talking about sensitization? When to let our explosive to gas to react. And what are the implications of it? Here, there's 4 pictures. Here is what we expect to have along the explosives column. Obviously, because of the pressure we have along the column, the gas, these very tiny little bubbles, they're gonna have different sizes. Depending on the location where they are. And the reason for that is because they're going to be under different pressures. The deeper you get, the higher the pressure. And for consequence, you're going to have smaller bubbles. And what is the implication of it? For those ones who already have worked with pump emulsion, there are differences between the first density you take in the cup. That's the sample when you are pumping. That's the sample you take straight from the hose and let it sit for a few minutes, and then we start measuring how much it is growing and how much it's going to weight once you skim off the top of it after it grows. So once usually the density of this emulsion before the gas is around 1.26 or 1.35, 1.36. So that's the first cut, which is the time 0. Once you let it react, by the end of 30 minutes, probably that's what you expect to have. This sort of situation in which you have to skim off, cut off, stop excess, so you can keep the same volume. So if you know the volume, you know how much it weighs, you can know the density. So you can weigh it to see what is your cup density. Let's say if you have a density of 130 at the time 0, once you let it react, maybe you can get a density or specific gravity of 1.002. But the question is this density the same all along the glass column? No, it varies for the very same reasons you were just talking about, because of the pressure that grows all along the explosive columns. You're gonna get smaller bubbles around here, and once you get smaller bubbles, you're gonna get higher densities. Here is just a video just to show how important it is, or what is the right procedure when you're using current emulsion. How fast you can cool the holes when you're charging the holes with water, and what are the consequences if you do not do it properly, or if you do it too fast or too slow. What do you guys think might happen? I'll show you. Hopefully it's going to run, like you said. Okay, let's start the other way. Just give me a couple of seconds.
This is an example of a floating primer with the nozzle and primer are located on the bottom of the hull. As the product is pumped into the hole, it may get under the primer, causing the primer to float up before the explosive detonates. In an effort to overcome floating primers, the hose
do you think would be the most appropriate? A, B, C, or D? C? How do we achieve C? In the case of, let's say, we are using ample, how can we take some of this explosive out of the glass? Some people use water, for example. This is an option, but is it a good option for ample? Look, and as we said before, ample highly hygroscopic, and probably it won't, if you dissolve all the way to the bottom part of the column will be dissolved. So there are a few options here. For example, high pressure air blow pipe. In some countries it's not permitted. For example, I don't know, even in Brazil you are allowed to do that. I'm not sure. But for example, that's the beast. You can use it even for a misfire. You can put it on the top of the glass hole and take all the stand and explode it. It has to be used with careful, obviously, because they are alive, primary inside of the glass hole, maybe. That's an option, and there are some other easier ways to do it. For example, in Brazil, when you are using pump emulsion, you can use a plastic tube, big one, exposed, and the bottom part, and we push it inside the hole. Obviously, it has a smaller diameter, and there is a rope, a little rope at the top of it, and we push it. Once it gets inside the explosive column, some of the explosive will drop inside this plastic tube. So we pull it back again until we reach the land we were playing with. As an option, we can use, for example, a sort of syringe. With this plastic tube, there is a ball on the top of it. We can open the ball, push it, close the ball, and pull it back, take it off. That's one way. Well, we have to be creative in this one. There's no rules in this one. We have to do what we can do in order to reach proper land. It's just a scheme how it works. And the most important of everything we talked about is have a system that works. Record it. This is very important. Have a system where you can put the date, time, location, block number, operators, nominal burden, spacing, all diameter, initiation method, or an area where you can sketch, where you can know any problem holes. This is very, very important. Record everything from the plan to the actual hole, to the actual loading charts. This is very important, even for legal purposes. In Brazil, there is a professional who has to sign it. So if something goes wrong, they're going to find that one who was in charge or charging. So this is very important. In summary, we talked about loss charging, the preparation, how we deliver, and the most important, how we record all these actions and all the parameters. Well, I think that's it for now. I'll pass the microphone to Andrea. Thank you, everyone.
Pouco aí.
Explosives and the properties, how to load the loads, how to charge. Let's talk about the initiation systems. Is how to connect, how to tie each blast hole with the other in order to achieve the proper fragmentation, the good vibration control, and all the environmental issues that we need to control in our blast. There are some examples of old products. We won't spend too much time on that, and we'll focus basically on the technologies that are more in use here and in other countries in the world. We'll talk a little bit about the signal tube, the system components, how to use it safely, and we'll talk in more detail about electric detonators, detonating cords, non-electric detonators, and the electronics detonators will be another topic. What is an initiation system? It's a way of detonating high explosive charges reliably at a specified time and in the correct sequence. When we prepare the blast sequence, we need to consider these three aspects here: reliability, time, and sequence. How to initiate? In the past, before the safety fuse, blasters used acoustic quill stuffed with black powder, and to start to initiate the explosive charges. But in the 1830s, the safety fuse started to be used regularly. And then the plain detonators, the instant electrics, and in the 19th, the delayed electric detonators. Here we start talking about delay and timing. Detonating cord, and look at this gap. And then the shock tube that we are used to use these days. Basically, we use more the detonating cord and the shock tube so far. Is that what you are used to use? Yeah. And in the 80s, the electronic relays. We have some mines that are migrating from the shock tubes to the electronics in terms of precision, safety, and the easy to do the job. The Excel is the commercial name for Orica products. So when you see a box or a detonator Excel, you immediately understand that it's a non-electric detonator. It's composed by a shock tube connected with a detonator. You will see how to construct it. There is a delay detonator in one end of the shock tube. In the other end, you have a chain hook to connect the detonating core, if you want. A seal to avoid water to come into the shock tube. the shock tube itself, and the sleeve showing some information about length, batch, date of manufacture. Important information for those who control the magazine, for example. This is typically a shock tube construction. Okay? It has a small diameter. It's about 0.5 centimeters, half a centimeter or less. It's a plastic with a void inside. And in this void, adhered to this internal tube, we have the explosives components. Okay? So it's a plastic tube. Inside there is a void, and the explosive is adhered to this surface. When you initiate it, the shock wave starts moving in this direction. The shock wave goes first. You see that HMX and aluminum dust adhered in the internal surface of the shock tube, the flame front. And there is dust here. Because of the firing sequence, it forms a dust of this product. Okay? Along this, so many years using shock tubes, we investigated some misfires. The manufacturing process needs to be very, very cautious about avoiding any other contaminant. We already found in the past, how can I say, a wing from a bee, very small insect parts inside. So we need to protect everything inside the manufacturing plant. If you put a lot of dust, this migration can block the void and interrupt the transmission. So this manufacturing process needs to be very, very well done in order to avoid anything here. Do you know the speed of the detonation of the shock tube? Not so fast as the detonating cord. It's not instantaneously. 2,000 meters per second. If you compare to a detonating cord or a booster, that's 7,000. It's lower than the detonating cord and the booster. Okay? How it's constructed? You have the shock tube here, all the way inside until this point. You have a rubber plug. The rubber plug is to avoid water or other contaminants and to give some flexibility so you can move a little bit the detonator without cutting the shock tube. Here is the main crimp. There are some equipment to do that in the plant. It's done by a machine. But sometimes you may face some blasters might face the challenge to build it. You buy the shell, the element, the detonator, and you need to assemble it in the field. You need to be very careful when crimping, not to crimp in this zone, because here is the explosive. Okay? Always be careful with this portion, the last part of the detonator. I'm sorry about my voice. Here is a conductive cup, just to put the shock tube in the center of the detonator. Here you have two delay elements. These elements that gives the time. So when you have a detonators, when you see in the box, 200 milliseconds, the delay elements. It's for each time, for each delay time, you may have different chemical elements, different substances, and also different lengths of the elements. Okay? This one is the most sensitive explosive, is the lead azide. This is the primary charge. Why do you think this shape means? Why it's not square or a cylinder? Any clues?
It's trying to give a point charge.
Yes. Point charge. And there is another aspect. For safety purposes, to avoid to have this element that is very sensitive close to the shell. And the base charge is the PETN. I'll say it in the term means penta erythritol tetranitrato. PETN. Right? Is the pentolate of the same. Just how it can be the forms that you can purchase. This circle, some of the shock tubes have an 8 format. Different lengths, different delay times, different connectors, everyone for each purpose. Every initiation system has a starter unit. To start the blast remotely, it might have surface connectors to distribute the signal and delay timing across the surface of the blast. Downline unit, the one that goes inside the blast hole, transmission of signal down the hole and delay timing. And the primer, the boosters or the cartridges, amplification of detonator energy to initiate main explosive charge. It's a sequence. The key is to have a good starter, what you use to initiate the whole blast. And also each blast hole. The surface connectors to distribute the energy, and the transmission inside the hole. Could be the electric, could be a detonating cord, could be a shock tube, depends on the application, depends on the availability of each product also. But we have discussed a little bit the implications of using detonating cords downline, for example. It damages the standing zone. It can reduce the energy because it damages the explosive column, and the initiation of the explosive can be up to the bottom, from up to bottom. Some of the starters, are not in use anymore, but the leading line is a shock tube that you can connect to the first glass hole in your sequence, in your blasting sequence, and you go to a safe point, 500 meters, 200 meters, depending on where to be safe, and then you initiate the shock tube with a proper tool. Connect the line is the detonators in the surface to connect one blast hole to the other. Blast pad, I really didn't see it in use, but it's a tool to remotely fire Excel using radio frequencies. I'll talk a little bit about that, but I didn't see anywhere using it. The Excel, the electric detonators. We talk about some electric detonators and captive fuse. We also need to consider cost-benefit evaluation to decide which one to choose. In terms of cost, of course. In terms of safety procedures, your neighbors, if you can blast without any concern of noise, air blast, fly rod, vibrations, you have more flexibility to choose the best for your operation. This one is the leading line. You connect the detonator in the first hole of the sequence when the holes are all tight, and then you go to a safe position to boom. You can find different lengths depending on the local market. 200, 500, 700, 1 kilometer. It's difficult for the blaster to walk through 1 kilometer to get to the starting point. Right? Connect the line. Take a look at that. Be careful. This also is an accessory that I don't see in use anymore. I saw a little bit in the past. It's just when something wrong happens or you need to cut the shock tube and you put this accessory to connect another shock tube. But it's not so practical. And then you take it for water to give water resistance. Surface connections, detonating cords, non-electric system, and harness wire for electric and electronic initiation. The connector bed. Have any one of you worked with this system before? Surface delays. You have a connector here, up to 6 shock tubes you can connect to the system. There are delays from 9 to 200 milliseconds. The length from 3.6 to 18 meters, and depending on the size of the geometry of the blast, if you have burdens and spacing really big, you use bigger tubes. It's color coded. Basically, the same construction of the detonator that goes inside the glass hole. The difference is that you have the explosive charge is only the lead azide, 210 milligrams. And if you remember, the detonators that go inside the glass hole, they have the lead azide and the PETM. Together, it's almost 1 gram of explosives. And this connector that to be used in the surface, it only has 210 milligrams of lead azide. Which clip first? Is there any sequence you need to follow to clip the other shock tubes? The one that goes inside the glass hole downline, or the surface to the glass roll behind or forward? Surface first and then downline. Where to start? Normally, we recommend to start connecting the last hole of the sequence. Here you have 3, 6, 9, 12 glass holes. This is the number 1 hole. We'll fire first, but it's the last one to be tied. So when the blaster is in the field, it's safer to start from the last one, and then the second, third, and then the first row. From the last row to the first row. But you can develop your what is relevant for you. All blasters may have a different procedure, which is different but always also safe. Downlines. The same system, use it in the surface and use it in downlines. I won't be this Endura that these names are used in Oregon and Australia. They are not used in Latin America. So forget about it. It's just a shock tube, a non-electric detonator. Number 8 detonator. Standard delays up to 4 seconds, for more than 4 seconds. And the lens used for the coal market to initiate an explosive. But you can use not such a powerful detonator, less energy, number 2 for example, to initiate other shock tubes. Detonator sensitivity. Do you think that 20 kilograms object falling in a detonator can initiate it? Yeah or no? Or maybe? Yes, it can initiate. It's not common. It's not common, but it can. But basically, it can be damaged and not properly. And what about cigarettes? shock tube. If you intentionally use a cigarette in a shock tube, what do you think it might be initiated? Yes, it's possible. We cannot assure, right? It's possible. When we talk about explosives, we need to say that everything is possible. When we get one business with Votorantim, an important company, the quarry and cement business in Brazil, they have old magazines full of products of 20 years, 30 years, old products, and someone needed to clean up the mess, and I was responsible for going in one of the magazines to destroy the detonators, 1,000 detonators. We used a crew, and when we would do the first blast, we prepared some holes, not loaded yet, not with the scissors, but to cut the detonators, cut the tubes, and put the detonators inside a cartridge, and put it inside the blast holes, and then charge with bulk emulsion to destroy that. And the shock tube, the excess of shock tube, put together, and it's a procedure to destroy with fire. The box is the plastic and the shock tube, and the fire started initiating the shock tubes. You could listen to the shock tubes detonating. And for mistake, I forgot 2 or 3 detonators. But the area was isolated. No one was close. And then, BAM! The detonators with fire. Be careful, always. The PTM can suffer something in this temperature, which is not difficult to get. 120 to 130 degrees is easy for a barbecue. What of these impacts you think may fire a detonator? Which of these? Rock falls? Maybe. Depending on the size, the weight of the rock, depending on the position it hits the detonator. It's unlikely to happen. Very unlikely. Pinching machine. Drop object. Same as a rock, depending on the size of the object. Unlikely to happen. Tools. This is important. Drive. If a light vehicle, a pickup truck or a light truck passes over a shock tube, this is a damaged detonator caused by jamming into hinge of charged vehicle. So you see, it has a lot of resistance, but it could have fired. This other one was recovered from a misfire in New Zealand in a construction job. And the damage was caused by severe acid groundwater. We talked a little bit about that. Static initiation of shock tubes. You know that? You know that even in our body we have static energy, right? Do you think it's possible for the static from a human body to initiate a shock tube? Very likely. Shock tube is not conductive. Can be conductive via the aluminum in the powder inside the shock tube. But a lightning strike may initiate silent tube. We have, in the last 20 years, 3 cases around the world. Initiation by lightning. The lightning, the right procedures, if there is a storm coming or a heavy rain with lightning, stop what you are doing, isolate the area, and tell your colleagues to go to as far as possible from the blast area. Yeah. This can happen not with shock tube, but it's more dangerous when you are dealing with electric detonators.
I just want to pick up on a point concerning the initiation from lightning. If you're in a mine and you're on a schedule, you're on timings, and you see the rain and so on coming, would you want to not protect the blast holes in terms of if you're already loaded with info, in case it covers up with rainwater and dissolves it, start to dissolve it, and then maybe you start to think of that risk, and you're trying to mitigate it, but then at the same time you might have the other risks that could be occurring if the pattern is already tied up. So what would you recommend to be the first best practice that should be followed?
It's a difficult situation, and the blaster need to take a decision quickly, right? If you are loading, if you are in the middle of the loading process, and you see that there is a storm coming, you have time to recover all the stuff, pack again, put back in the truck all the non-used explosives and accessories, and isolate the area and leave, right? But if you have the blast already tied, just waiting for the evacuation process, maybe it's better to fire. If the area is done and the isolation is complete, you have the okay that no one is close to the blast area, it's better to fire. Or in all the sites we operate, and not all the sites, but it depends also on the customer, on the negotiation, but most of the customers are willing to install the storm detector. So there are some equipment that we put in our blast sites, and the site supervisor has all information if there is a storm coming in the next half hour or next hour, and if it comes 10 kilometers away or 50 kilometers away, so we have more time to take the decision to rush and finish it and fire, or stop and remove all the people. Impact initiation of signal 2. So every time you are working, it's better to avoid the situation. Working very close to the bench, you may face some rock falls. And now, this situation is unlikely to happen, but we have some we have one case of a blaster in a copper mine in northeast of Brazil that was injured by a rock fall in an open pit mine. He was working close to the crest, and the rock fell into his shoulder. Almost died. Almost died. Big piece of rock. It's not only dealing with explosives, it's taking a look at the whole environment. This is one glass hole that fired due to this snap, slap, and shoot. A wheel of the light vehicle grabbed the shock tube, initiated. What would happen if a detonator fired in a 150 millimeter tin can? I need to advise you, the next slide is not beautiful. If anyone do not feel comfortable seeing some blood, do not look. No, really. I know that some people don't like to see it. It's the hand of an operator that was handling a detonator and it fired. If you don't like, don't look. It's important to give us a message of safety. I don't know the cause. I don't know exactly the cause. Some potential causes. Maybe there is a misfire. The detonator got stuck in the blast hole and he tried to pick up. I can tell a real case in a plant in Brazil. There was a bunch of 10 detonators that during the manufacturing process they detected some problems. They were there to be disposed. Yes. And one operator with the best intention threw some compressed air, but the shock tubes were opened. The operator has lost 2 arms with a bunch of 10 detonators. So you had there 10 grams of explosives concentrated, and he lost his arms. He's alive. The accident was in 2006 or 7 in our plant in Brazil. So really dangerous. If you follow the procedures, you'll be safe. Electric detonators. I don't know, do you still use electric detonators here in Guyana? Not anymore. It's an old practice. We have one customer in Brazil that still uses electric, and some of the seismic industry, they buy electric detonators because of the procedure for investigating oil and sands. There is a base charge similar to the non-electric detonator, and the fuse is protected. Here is a closer look. The fuse head is protected by a metal foil. a solder for the leg wires, and a closure plug, and the green. Very similar to the non-electric detonator. The difference is that in the non-electric detonators, it's a chemical energy, it's a detonation inside the shock tube, and here is the electric source of energy. You can initiate it with a battery in the car. There are some ways with some firing machines. One bolt can fire this kind of detonator. So the battery inside this equipment can initiate this detonation. What sources of electrical energy here do you think are able to fire an electric detonator? Batteries I already mentioned, right? Power sources. It's electric. Electric equipment. Cables. Conductors, lightning, ground currents, static, radio, cell phones, wiring cables, power lines. There are procedures for everything. If you look at the technical data sheet of an electrical detonator, you will find how to protect from each source of electrical energy. Including in our blasting procedures, we recommend not to enter the blast area with cell phones, radio. If you need to talk, go a little bit far away from the blast site, right? There are cases of initiation of detonators with cell phones. It's more of the same slide, right? The blaster has the responsibility to have a wider view, take a look at all the aspects that might influence the safety. If you are working close to power cables, high voltage, induction, take care of people who is going to enter the blast area, to not use radios and cell phones, all sources of electric energy, earth leakage, big machinery, electrical machinery moving inside the mine.
Just one observation. You mentioned ground current. Some of the lithological types that you may have high induced potential and high chargeability rates. Would that be a risk in terms of potentially causing an initiation?
Good question. Very low. Very, very low. Mm-hmm. To avoid misfires using that connectors, right? To connect shock tubes, use clip and slide technique. Clip and slide. Never double wrap tubes into block. It's not a good practice. We have investigated some misfires due to double wrap. Right? Only one. Clip and not double wrap. Always check hookup. We investigated some misfires that the base cause was human mistake. Someone forgot to clip the shock tube, and the blast hole did not fire. Or it's in the graph that Victor showed some slides ago. If there is a sequence and one of these is interrupted, the rest of the sequence won't go. Always bury starter deaths. It's a good practice if you need to protect from rockfall, damaged objects. Bury starter. This equipment, I didn't see it in operation. I know it exists, but I don't know if someone is using it so far. It's a machine that remotely fire shock tubes via a radio link, coded radio link. It's a plastic machine, two-way radio communication. There is a controller and a receiver. The receiver stays close to the pipe, to the first blast hole, to the sequence, to start all the sequence. It receives the sign from the blast machine, the blast command, and spark fires itself. Some details we don't need to be taking a look at that. There is a separate chapter that we would talk about electronic plastic systems. It's really interesting in changing the way the miners are planning the blasts. In sensitive environments where you need to take care of vibrations, the precision of the delay times gives you the flexibility to control the vibrations. In mines where the fragment, you need more and more fragmentation, more fines, you can use short timing between blast holes. It means 1 millisecond to up to 4 milliseconds between the blast holes to make the most effective interaction between the shock energy of the first blast hole and the second one, creating more cracks in the rock. So there are lots of applications for electronics. We will see it tomorrow. 12 lines in the manufacturing process. The explosives goes here inside, and there's a plastic cap to protect against water, giving flexibility. So you can cut, you can make some knots and tie your entire blast. In some very cold weather, it's recommended to use that quartz with wax overcut to give, because the plastic can freeze in cold temperatures and making it difficult for the blaster to tie and to use the cord. You can use the detonating cord in the surface, putting together with the J-hook of the non-electric, every single blast hole, put it together in a line. You can fire line by line, reducing your costs of surface delays. Or if you have some vibration restrictions, or depending on the blast design, you can use some delays between each blast hole. Depends on the blast plan. you can use the millisecond connector. The millisecond connector, when you tie this way, the detonating cord destroys its first detonator. The energy passes in the shock tube, and this detonator gives the time. So the MS connectors, millisecond connectors, you need 2 detonators with the same delay timing. Let's say it's 25 milliseconds. You have one detonator of 25 milliseconds here, and the other one the same here. The first one is just initiated instantaneously by the detonating cord, and this one gives the time, the sequence. The detonator is the same as shown previously, with the delay element, led aside. And you can design your blast considering this delay range. If you have a very hard rock and you need short time to improve fragmentation, if you have soft rock or plastic rock, such as a limestone, for example, you can use slower delays. It's important. This kind of accessory is recommended only to fire other detonating cords. Do not clip another shock tube here. How to do it? How to do the knots? Double globe hitch. Reef knot. This one is very strong. When when you finish the product, you need to connect another one. Use this knot. It's a lot of tensile resistance. Always try to use 90 degrees angles. Do not use short angles. It might generate a cut. Cutting the detonating cord, plastic jaw. There is a specific tool. We can send a picture later. Knife. Be careful. We recommend always, if you have a knife, don't use scissors. Do not use scissors to cut any accessory, because there are 2 metal parts, and you may have some dirt, and it can generate some friction. Right? Do not use scissors. If you use a knife, use it in a wood surface. Put the product in one way. Don't do that. The detonating cord has a strength of 70 to 100 kilos, 10% stretch, compared to the signal tube. Impact resistance, 20 kilonewton. VOD, 7,000 years is meters per second. Water resistant and oil resistant. They are a bit tougher than the shark tooth. Yeah, just curiosity. In Australia, if you put a detonating cord from one to city, yeah, it will take 9.5 minutes to get from one end to another. We are talking about 5,000 kilometers, more or less. From São Paulo, where I live, to Georgetown. I think it's the same distance. Misfires. Always be aware, not leaving loops can cut. The detonation is coming from this direction, and it may cut here. So this blast hole or this accessory will fire, but when it comes here, this one you will have a misfire. Always be aware not crossing detonating cords if it's not planned. The same as this way. You need to form 90 degrees angle to avoid misfire. The same. This one is okay. You have a continuous line. Do you think this one will fire? Because it's the detonating cord fires for both directions, right? Do you think it will work here? Be careful not to tie very close to the end, because when you put the detonating cord, there is no protection against water. So it will start absorbing water. Put the detonator away from this part that may be contaminated with water. What about this? Will it work? Yes. The same. Be careful. If you are firing from this way to this way, be careful not to leave the shock tube close to the detonating cord, because the objective is when the detonating cord passes through the J-hook, it will initiate the shock tube here. But by doing this way, the energy or fragments can cut here the shock tube, and you have a misfire. Don't forget to connect. The geometry, same. You have short angles, small angles, or you can have a cut off in this tube. Near knots. Be careful. Also, if you have the detonation coming from here or coming from here, be careful not to put a shock tube too close to the trunk line. When you have the shock tube in the direction of the detonator, be careful. It may throw some fragments of the components of the detonator, some fragments of rock. There is some possibilities of misfire, of cuts. Any questions so far?
Yes. I can speak everybody. Deal with the safety range, right? In the field that I had, say safety range from the blasting area would be like 3 to 500 meters away. I just for like 20 meters wood. I only talk about 20 meter wood. Right? It will have alpha elastomer framework or exposed can work with it. But the safety range be the same for a 20 meter wall and 100 meter wall.
Yeah, we had some discussions recently with a customer that told us Orica had caused a fly rock and the rock hit the drilling machine. And then when we measure the distance, it's okay with the distance the customer considers, but it's inside the area that Orica considers unsafe. So there is always need to be meetings to discuss about the safety distance, the range of, and for each product you may have different distances. We consider the worst case scenario. We consider 600 meters for every product, at least in Brazil. We consider 600 meters as a good isolation area. Okay? But if you're only dealing with one detonator and need to test, you don't need to be so cautious like this, right? If you are dealing with one booster, it all depends. Remember that sensitivity increases. The most sensitive product is the lead-azide, and then you have the detonators and the boosters, the dead core, and the explosives. When you go up, you need to be more careful because it's more sensitive. Otherwise, depending on the amount of explosives, I'm talking about a lot of accidents, misfires. Let me tell you another story. In 2004, our package emulsion plant blown up. 3 dead. Some houses. It was about 2,000 tons of explosives in the storage, and some houses in the other city, 5 kilometers, had the windows. The windows broke. So it always depends on the type of product you are dealing and the amount, the quantity that you are dealing. We completed the schedule for today. Uh, but we would like to have this 20 minutes, if it's not so bad for you. There are some images until 5, right? We have 20 minutes to 5.
All right, that's the way now. Okay, so it won't take much longer now. We're almost at the end of our activities for today. But what I would like to show you guys is one of our tools. It's called Shotgun. This tool is used to design blocks for open pit, and it has several features, such as you can build surface, calculate volumes, you can rotate it freely, like this, so you can see how the mine, how are the mine topographies. And you can use, obviously, you can use it for designing your blast plan. Maybe we can go through some block designs really quickly. That is, if already have one. Hang on. There we go. All right. So what we intend to do tomorrow, we're gonna go step by step on this one. First idea is for you guys to have a good idea and have the introduction to these block designs assistants, such as block shuttles. There are some other ones in the market. I think the second most famous one, shuttle, obviously, will be the JK Seagrass. Okay. Just a quick for example, let's try to do a quick blast design. Let's draw a baseline. I'll explain maybe tomorrow step by step, so for those ones who are interested about knowing a little bit more about this software, again, we can talk a little bit further tomorrow. So, for example, if in your operation you have, let's say, a glass, you have to design this one, let me see, is only almost 90 meters. So, for example, if I need to design a quick, I can use these two, and I can insert what is going to be our burden, for example. Let's say 5. Our spacing, let's keep it 9. How many rows? It's only 5. And here we can choose what's going to be the loading. So we can add all the explosives and all the initiators. Let's start with let's say we are going to use info. So I can pick, which is called Amex. And let's say we're going to be using a 4-6 meter standing. Here's air. My computer, it is in Spanish. So. Oh, let's Excel 475 milliseconds as a download time. And they boost. No, let's say 450. And okay. Okay, and add. It's okay. There is our class design. So from here, you can see the length, or you can see just the color if you want. The whole ID, you can change it pretty much almost any parameter in this program. And obviously, there are some other pretty cool features. Let's say this is your press. So if you're logging on a small bench like this one, you can use this software to help you understand how your charging design. And tomorrow we're going to see in a little bit more detail how we're going to connect it, how we're going to be firing it. Let's choose one point of initiation here. Okay. Now there we go. Alright, so let's say we're going to start our blast from here. What I want to see. So let's call it initiation point. Tomorrow we'll be talking step by step. It's just to show you that it's very interesting. Okay, so let's choose our product surface reference. So Excel. So let's say put you the 9 milliseconds. $17 and what else? 42. And it's pretty easy. Using this software, you can just pick what the data you want to use. Choose the first call and drag it along. So you have the first line, and then use the reverse rule of thumb. Reverse. Forgot the name in English, but tomorrow we'll remember. The only thing you have to do is just push it like this. Let's know what. Here we go. So there we go. Now we are connecting. That's the reverse rule. That's pretty cool. So after you finish doing all your design, you can print it. Not only the sketch of the glass, you can print all the quantities you're going to use it in this glass. In other words, how much explosives, how many XLs, how many boosters. There we go. there are some few rule of thumbs you have to go through in order to make these connections. I'm going to talk about it. Still have a few minutes here just to show you a couple of things. So, that's the cool thing about it. Here is one tool that's pretty useful, so you can see how fast your burning front is going before your first blast hole goes off. So just for you to have an idea. Begin. And then you see all the products on the surface burn first, and then the first blast hole went off. But it took too long. We can change it as well. So that's the good thing about this tool. You can check anything you want to change in your design before doing it on the bench. So you can check test any changes and see how it's going to look. Then what else do you think is important to check besides on quantity? The angle of initiation. So that's how of your angle of your in this particular design. Here. And last but not least, first method. That's how it's going to look. What about if we change? As we said, this one, 475 was too high for this particular house because it took too long after the burning run finished for the first hole to detonate, so we can change it. Here. Let's say let's use 275. Okay. Let's check how it looks. There goes burning front. And then you can see just before the burning front reaches the last hole, this hole here starts detonating. Alright, there's a lot of things you can do with this software. It's just a glimpse for you guys. Maybe tomorrow we can continue. Well, I think for now that's pretty much on the scale. I don't know if there is anything else to say. If not, thank you all guys for your patience. Thank you for being here. And see you tomorrow.